Okay, you hear me? Yes?
Yes.
Okay, so good morning, everyone, and thank you for giving me the opportunity to show these results. So I will speak about tomography on coccolithophores. So coccolithophores, what are they? I'll try to change the slide. Okay. Yes, so coccolithophores are unicellular algae, and they have particular features is that they exhibit an external calcium carbonate skeleton. So you see here a picture of one of this external skeleton, which is called cocosphere. And this cocosphere is made of different plates, which are called coccolith. So here you see a cell which produces one coccolith inside the cell. So the growth and the nucleation and the growth comes inside the cell. And then when the growth is finished, the coccolith is expelled to form a part of the cocosphere. So we can estimate that the production of coccolith is around 1 coccolith per 2 hours. The formation of the coccolith takes place so inside the cell, and we can show by using X-ray cryotomography that the nucleation of coccoliths begin to form a proto-coccolith, which is located at the surface, at the in contact with the nucleus of the cell. So here you see the beginning, the onset of the coccolith, which is called proto-coccolith, and it is formed on the surface of the nucleus. So the quantity of coccolithophores in ocean is very important in such an extent that we can even see them from space images. And it is quite easy to understand why they are important in the carbon cycle. So they produce, they absorb a lot of quantity of CO2, and they produce large quantity of calcium carbonate. So large quantity of calcium carbonate, and this quantity fills the deep of the ocean, and then so we can see that the cliff, for example, in Etretat is made of this agglomeration part of this tiny skeleton. So researchers are interested to forecast what will be the destiny of these coccolithophores in a high CO2 world. Maybe you know this, but if you increase the CO2 concentration in air, the consequence is that you will decrease the pH and decrease the concentration of carbonate in the ocean. And this may lead to a reduction of the calcification rate. So it's true for corals, for echinoderms, and it seems to be true for foraminifera and coccoliths also. So for example, here, Beuvier and co-workers have shown that if they collect from the ocean coccoliths in a region where the ocean displays a low concentration of carbonate, the mass of the coccolith is small. And if they collect coccolith from regions where the concentration of carbonate is important, the mass is more important. So it seems that there is a correlation between the mass of the coccolith and the concentration in carbonate. To measure it, it is very challenging because the mass of the coccoliths is in the order of few picograms. So the method which is used now is the polarized light microscopy. So by using this method takes advantage of the birefringence of calcite to measure the intensity in cross-polarization. So our first objective was to check by another technique, that is to say by tomography, that the measurement done by PLM to measure the mass were correct. So our objective is to check that the measurement of the mass of the coccolith are correct. And we use tomography. In particular, we use CXDI. So CXDI is one type of nanotomography. It's for coherent X-ray diffraction imaging. How it works? So several coccolithophores are put on membrane, a very thin membrane, and only one is illuminated by X-ray beam, which is a coherent X-ray beam. And we collect the diffractive intensity on the 2D detector at 4.2 meters from the sample. Then we turn the sample and we obtain several images, several 2D patterns, and then we assemble these patterns to obtain a 3D diffraction volume. And then, using a phase retrieval algorithms, we were able to convert this 3D diffraction volume into 3D real space volume, with here a voxel size of around 30 nanometers. So once the measurements with CXDI were done, the idea is to check that our reconstruction are correct, are true. So we take care to check by observing them by SEM that the reconstruction by CXDI were correct and the agreement was quite nice. And we did it for 7 species of Coccolithophores. So here you see 6 more coccospheres coming from 6 species of Coccolithophore. And next, because the idea is to compare our results with PLM, with polarized light microscopy, we need to extract from the coccosphere the coccoliths. So we extract them step by step, for example, here on a given species. And we did it for all the coccospheres that we observed by nanotomography. And so to compare with PLM, we need to extract parameters, and we select 2 parameters. First, it is the major axis, which is quite easy to obtain as well by nanotomography and PLM. So this major axis is ranging from 1.6 to 6 micrometers. And the second parameter is the mass. So we extract the mass by assuming that the mass is the product of the volume by the density. And we choose the density of calcite 2.67 grams per centimeter cube. Then we can plot the mass in y-axis as a function of the major axis. So the results are in black dots correspond to the nanotomography. So here, for example, it's the mass of the smallest coccolith of this species, and this one for the bigger one. So we did it for the 7 species that we measure, and we compare these results to PLM. So PLM results are in color dots, and CXDI are in black dots. So the agreement is quite good, and validate that the measurements done by PLM are correct. The second thing that we study is come from the fact that within a single coccosphere, you see that there is a big distribution of mass and size. So we try to understand the origin of this large distribution. The first thing we can mention is that the coccoliths are made of a central area called a grid, and we measure the perimeter of this grid. And we plot the mass of each coccolith as a function of this grid parameter, and we see that there is a positive correlation between these 2 parameters. why we take care of this parameter, it is because when we look at inside the cell, when we look at the protococcolite formation, the formation begins with this region, with this ring. If we extract, for example, this ring, we have a second information is that we observe that around this ring there is a, oh, I don't know, yes, there is a periodicity here which corresponds to the beginning of the formation of the monocrystals of calcite. These monocrystals are called segments. So it's not very easy to segment each segment, each monocrystals, because the resolution is slightly too low, but it is very easy, very simple to count how many segments there are for each coccolith. And so we can plot the grid perimeter, the perimeter of the grid, as a function of the number of segments for each coccolith. And we see a linear relation, which means that, in fact, the conclusion is the width of each coccolith is constant, whatever the species and whatever the coccolith, and is equal to around 115 nanometers. So it's interesting because we can combine the two previous relations in order to have one relation, a new relation, linking the number of segments of monocrystals that we can count with the mass. So we just need, from this relation, we just need to count how many crystals there are in order to have, in a forced approximation, the mass of the coccolith. If you plot the graph, you see that there is it works pretty well for the different species, except for one, which is Emiliania Huxley P41, for which the mass is not determined only by the different segments surrounding the grid, but also by the calcium carbonate, which is formed inside the grid. So according to our relation, which is here, the mass is slightly underestimated because of the presence of calcium carbonate inside the grid. The other things that we observe is when we look at the coccolith on the side, we see that there is some curvature, so they are bent. And if we remember that coccoliths are formed in contact with the nucleus of the cell, we can propose that this curvation comes from the curvation of the nucleus. That is to say, if you have a big nucleus, you form a big coccolith, and if you have a small nucleus, you can form a small coccolith. And the other thing is that the coccolith is not in direct contact with the nucleus. There is an intermediate, which is called organic base plate scale, shown here in yellow. And it's an organic support. And in literature, some researchers report the existence of this organic base plate, notably for this species, Pleurocrisis carterae. And they prove that the nucleation of calcite happens all around this organic base plate. You see also the fibrous structure of this organic base plate, and these fibrous structures look like the one of the grid of the coccoliths. This fibrous structure can be also seen by AFM here, and this leads us to propose a mechanism of formation of these coccoliths, with first an organic base plate, which is on the nucleus, and which contain at its periphery several nucleation sites, each site, the distance between two sites is around 150 nanometers. So it's due to the formation of nucleation of calcite, one site every 150 nanometers. Then these small crystals grow before being expelled outside the cell. But to explain why there is such large polydispersity, maybe we can propose this scheme. When we look at the life of the cell, just after the mitosis, just after the division of the cell is small and the nucleus is small, and we can imagine that the coccoliths, which are formed when the nucleus is small, will be small. Then here it is expelled, and during the life of the cell, when the cell grows, the nucleus will be bigger and will form bigger coccoliths. So we propose this correlation or this link between the size of the nucleus and the size of the coccoliths in order to explain this large polydispersity. Okay, so to conclude, CXDI was able to image in 3 dimensions single focospheres from which we were able to extract the different the 3D geometry and the mass of the coccoliths. We confirm that the mass obtained by PLM is correct, and we find a new relation linking the number of segments with the mass. So it's worked pretty well for 6 of the 7 spaces that we studied. And finally, we propose a correlation between the size of the nucleus, the size of the organic base plate on which the nucleations take place, begins, and the size of the mature coccoliths. Okay, thank you for your attention, and if you need more details, you can look at this article that we published quite recently. Thank you.
Great. Thank you, Tom.